So in this portion of the section, we're still talking about the alternating series test, but this is quite possibly, I think, the coolest remainder theorem you'll ever see. If you remember back to the integral test, we had a remainder theorem that said we had a remainder theorem for the integral test. If we just kind of review a little bit, that said, let's treat the series as basically this continuous non-increasing function, and let's, cut the partial sum here, and then this stuff that's out here is the remainder. Remember that? It's the stuff that we didn't add to the sum. We just added all this stuff up. So this is adding all this stuff would be our, oops, let me change the color back to green. Adding all this stuff would be our partial sum S sub n, and we stopped adding terms here, and this is our remainder. And so to calculate this remainder, we had to do this complicated, from n to infinity and integrate this whole thing. And then take, it was improper, so we had to take a limit as b goes to infinity and find out if we get a finite value. And it was pretty involved. And so when we talk about the alternating series test now, let me try to fit this on one screen. When we talk about the alternating series test, this is the really the cool thing. And that is, let me just make this tinier. There we go. So there's the integral test. So now when we're talking about the alternating series test, this is looking a little different. This is now looking, this alternates. So this, instead of looking like non-increasing like this starts to look like a positive term, a negative term, a positive term, a negative term, a positive term, a negative term, and it starts to dampen just on its peaks like that. And so when we talk about this alternating series, then what we really have is we have fluctuating positive and negative areas for the remainder. So if we stop counting terms here, then this remainder per se has a little bit here and a little bit underneath here, and so the idea of this remainder then, this remainder never gets bigger than this next term here, this an plus 1. Because when we subtract an plus 2, then we're going to take away from this value. And when we add an sub 3, we're not going to get back up to this value. So this is the biggest piece left. And so what that means then is if this is the biggest piece left, if we stop counting the sum here, this has to be the maximum remainder we could possibly have, which I think is kind of cool. So when we take a look at this, and this is kind of a, a little better drawing of what's going on the previous page than I could draw myself, but basically it's saying, if we look at, let's look at 1 over n squared and the alternating series over n squared. And so if we look at this, this is 1, 2, 3, 4, this is the 4th term. So we're talking about 1, 2, 3, 4. We're right here at 1/16th, so 1 1/4, 1/9, 1/16th, 1/25th, 1/36th, 1/49th, 1/50th, and so if we look at S sub 6, then we're looking at 1 minus a quarter plus a 9th minus a 16th. This is 1, 2, 3, 4, plus a 25th minus a 36th. And so there's your S sub 6. And then if we then look at what's left here, okay, we're going to have plus a 49th. And we're going to have minus 1/64th and plus 1 over 81 and minus 1 over 100 and plus dot, 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 dot. So the idea is that 1 over 49th minus a 64th plus a 1 over 81 is never going to get back up to 1 over 49. So we're never going to get anything bigger than what we see here. So if we never get anything bigger than what we see here, then the maximum remainder maximum has to equal that an plus 1 term. So for this one, the maximum remainder has to be a7, and we just plug in 7 here, and that's going to be, if we plug in 7 there, it's going to be, and let me qualify this, and I'll qualify this in a second. It's going to be minus 1 to the 7 plus 1 over 7 squared. And that's going to be 1 over 49. And when we talk about remainder, we talk in terms of absolute values. This ended up being positive anyway, but really when we talk about a maximum remainder, we talk about the absolute value of that next term. So we added up 6, we looked at the 7th partial sum. The 7th partial sum is 1 over 49. That's going to be the maximum remainder for that alternating series. So in looking at this alternating series, basically what the alternating series remainder is saying, and I'll just kind of recap it, the maximum error, the maximum remainder is going to equal the absolute value of that next term. And so what you'll see, how you'll see it stated in textbooks is we've got to satisfy the condition for an alternating series. So we've got to have this non-increasing nature. We've got to do the limit as n goes to infinity and make sure it's 0. And so the remainder then is going to be less than or equal to, okay, that first neglected term. So in other words, if we have a 6th partial sum, the first neglected term means the first term you didn't add after you found the partial sum. So the first neglected term would be a7. If we had a partial sum of S179, then the first neglected term would be a180. And so what we say then is, and this is kind of a way of saying it, here's our neglected term. That's as big as it can be, so our remainder is less than or equal to that. And this over here is saying this is the actual remainder. S is the actual sum, and S sub n is the partial sum. So this is the actual remainder. And so the idea is that if we can find the maximum remainder, then we're confident that the actual remainder is less than that. And that's really kind of what we're going after, is if we're okay with the maximum remainder being what it is, then the actual remainder being less, we should be also okay with. So let's take a look at this series here. It says, determine the number of terms required to approximate the sum of a convergent series with an error of less than 1/1000th. Okay, so we want our remainder to be to be less than 1/1000th. And so what we're really talking about then is we're talking about 1/1000th being the biggest it can be. So that remainder being less than or equal to that value. If we look at the series here, this is the actual sum of the series. So this is our S. Okay. And so what we want to do is we want to see how far out we have to add terms so that we are within 1/1000th of 1 over the square root of e. So if we just get a calculator up here, and just take a look at what the value of 1 over the square root of e is to 3 decimal places. So 1 divided by the square root of e there we go. 1 divided by the square root of e is, okay, so 1 divided by the square root of e is 0.6065. Okay, and so if we're going to be within 0.001, that means we're going to be within 0.6055 to excuse me, I said that wrong. We're going to be, no, that's right. We're going to be within 0.00655 to 0.6075. So here, if this is the actual value, we could be off by 1/1000th in either direction. And so, so what we have to do then is, this is the a sub n term. Remember, the a sub n term is without the alternator, so we ignore this. That's why we're looking at absolute values. Our nth term is 2 to the n times n factorial. So our n plus 1 term is going to be 1 over 2 to the n plus 1 times n plus 1 factorial. And so it's that expression that we get to play around with, 2 over n plus 1 times n plus 1 factorial, that we got to play around with to get less than or equal to 1/1000th. Or the other way to look at it, since the numerators are both 1, we've got to find a denominator, 2 to the n plus 1 times n plus 1 factorial, that is bigger than 1,000. So if we can make this bigger than 1,000, then we know this whole fraction is going to be less than 1/1000th. If that makes sense. And so the quickest way to do is to really graph this. And so we're just going to graph this expression. Hopefully I can remember where to find the factorial. So 2 to the power x plus 1 times quantity x plus 1, and I think factorial is under math and probability. Yep, down there, option 4. So I have 2 to the x plus 1 times x plus 1 factorial. And not that I need to graph it, what I really need to do is look at the table. So you're not, those are discrete values. It's not a continuous function because of the factorial. So it's going to have a value at 1 and at 2 and at 3 and at 4. And we're certainly off the grid, so I'm not going to worry about that at all. I'm just going to worry about the table. So if we look at this table, when n equals 0, put in 0 here, 2 to the n plus 1 times n plus 1 factorial equals 2. And so we're looking for when we bust 1,000, right? When we get over 1,000. N equals 1, so that's 4 times 2, 8, right? At 2, we're up at 48. I'm just reading off the table now. At 3, we're at 384. At 4, we're at 3,840. And so we found that point where the denominator starts to be bigger than 1,000. So when n equals 4, then the remainder is 1 over 3,840. Okay, so what that means then is this is the partial sum we need to get to. If we're looking at the series here of 2 to the n times n factorial over negative 1 to the n, and we're going from n equals 0 to infinity. Then we're looking at, when we put in 0, we've got 1 over 2 to the 0 times 0 factorial, that's defined as 1, minus 1 over 2 times 1 factorial, plus 1 over 2 squared times 2 factorial. So this is 0, 1, 2. This is the a sub 3 term, which is going to be minus 1 over 2 cubed times 3 factorial. And then we have 1 over 2 to the 4th times 4 factorial. And so this is our a sub 0 term, our a sub 1, a sub 2, a sub 3, a sub 4 term. And so if you notice, we've gone up to the a sub 4 term. That's what this means. Okay, this is an S4. But if you count the number of terms, this is 5 terms. And so if you notice, and we have this mismatch all because of this right here. We started at 0, and sometimes these series will start at 0, sometimes they'll start at 1. When they start at 1, your partial sum will be the same number as the number of terms. But when we start summing at 0, then we acquire more terms than our partial sum indicates. So we have a partial sum of S4, and that partial sum is comprised of 5 terms. So that's something that you have to kind of be careful of. So we have to sum up the first 5 terms in the sequence in order to get a partial sum that is within 1/1000th of 1 over the square root of e.